So let's move on to our next speaker, and our next speaker is Andreas Fertig. Andreas is a freelance trainer and consultant for C++, specializing in embedded systems. And since his computer science studies in Karlsruhe, he has dealt with the requirements and peculiarities of those embedded systems. He worked for 10 years for Philips Medizin Systeme as a C++ software developer and architect, and he's also involved in the C++ standardization committee, especially in SG14, which deals with embedded systems, obviously, and he develops macOS applications and is the author of cppinsights.io. And the fun fact about Andreas is that although he operates in a very fast-moving industry, he still enjoys his 26-year-old car, and his friends often ask him when he's going to get a new one. Let me ask you, because you know we've got a history of German cars being used in Poland. And no, I'm not talking about BMWs. I'm going back to 26 years ago or more. So let me ask you, that 26-year-old car, is this a Trabant or a Wartburg?
No, it's neither. Sorry.
Okay, so this is a question to be asked later. What is the old car? What is the new one? But in the meantime, C++ Lambdas Demystified. Andreas Fertig.
Thank you, Raphael. Yeah, hello and good morning. I hope you're enjoying Code Dive. I did yesterday. And it's a good thing if you have somebody who introduces you, but it feels odd if you're used to do your own introduction. So I'm Andreas. Hello. You now know that you can hire me for training and for consulting services. So, what can I say about me? What Raphael not already has said. My last name is a very German name, or a very German word, to be precise. It's an adjective. In German, you can translate it as ready, finished, or completed in English. Which is great, because people think that with your name there comes also a certain completeness of the project. It's not true, I can tell you. It also has some issues, because in German the adjective is spelled with a lower first letter, while as a name is spelled with a capital first letter. So that makes me constantly arguing with my spell checker whether I'm right or not. We are still discussing who wins that. Sad thing is, and it's okay if you now leave after I'm telling you this, but I have this name since I'm born, so for over 30 years now. And it took me roughly 30 years, a bit more to be fair, to learn that I mispronounce my own name. Okay? Because from the part in Germany where I'm coming from, I say it's Fertig, with more or less a K at the end, while in proper German it's Fertig. And I'm telling this story about my name for a long time, and all the time it's possible to collect stories. And the story this time is that Raphael here pronounces my own name better than I do. So, among this, and for all the good work Raphael does here, so please give him a hand of applause, because he does an incredible job.
It is actually very funny, because maybe I speak like 5 words of German, and by this pronunciation I just pretend that I do, which I don't.
It's terrific. It's terrific. So, okay, maybe it's better if I not talk about my name, more about C++. And this is the evolution of lambdas. Lambdas are the one thing which is highly targeted these days in C++, since we got lambdas in the language. If we go through this slide from the left to the right, from the top and to the bottom, then we can, in C++11, we have in the angle brackets, in the angle brackets first, we have the capture list. We can capture by copy in C++11, by reference, by name, we can capture this. We can capture parameter packs, and we can capture by named reference or named copy. In C++14, that all has increased, we can now also have something which is called init captures. This is the first thing here where I can introduce a new name of a variable I'm capturing inside of the Lambda. I can also capture the same system as a reference and not just as a copy. Can introduce a new reference name there. We will see examples about this later. And in C++17 there is something which is written star this or dereference this. We will also see what we can do with this. So this just was changed or added to the capture list. Next to the capture list we have a block which is empty until C++20. And there you can see the other angle brackets and the type name or t-perms. That's a good hint that now we are also able to have templated lambdas and write different code. We will see examples about this as well. Then in the parentheses, it's essentially a function declaration style. We can with C++11 say we like this lambda to take an int parameter, char, or our own class type whatsoever. With C++14 we got something which is, till C++20 is not out of the door, still unique, because there we can have auto as a parameter type. It's then called the generic lambda. We haven't seen anything like this so far. It will be similar with concepts. Next to the parameters of the lambda, we have the specifiers. We can say that our lambda should be mutable. With that, we can change all the copy captured values inside of the lambda. Otherwise, it's const by default. With C++17, there was another enhancement. Lambdas are now implicitly const expr. So if it's possible to do that thing what you like to do with your lambda at compile time, the compiler enables you to do it by implicitly adding const expr keyword to your lambda. And now is the hardest part. C++20 brings us a new version or new variant of const expr. It's called const evil, and because I'm not a native speaker, I always hope I pronounce it right, because it's not evil as in something bad. It's evil as in evaluated at compile time. It's guaranteed in comparison to const expr that it will be evaluated at compile time. Then we can add an exception specifier like no except. It was possible with C++11 already, and I had to strike this out with C++20. There was the plan to have contracts there, but unfortunately they were tracked out during the Cologne meeting, so there is no expects or ensures so far, but we are hoping that it will come back with C++23. Then we are seeing the trailing return type. It's optional because by default your lambda returns an auto type, but if you need or like to specify the return type of a lambda, then you can do so by the trailing return type. And in the last column we have with C++20 requires keyword, which comes with concepts. I'm always very proud of myself if I manage to get them right, because the 3 twos, coroutines, concepts, and contracts. Sometimes I confuse the C's here. Sorry about that, but it worked here. So then below we have in the curly braces the body of the lambda where we can write the functionality we like our lambda to have. And next to that, in the parentheses, the parameters or the arguments we pass to the function. That's essentially all the different things you can do with your lambdas. Now it's hard for me to see anything, but I've been told that more or less every attendee was eligible getting a t-shirt from the conference. And I'm not sure if you looked what's on the shirt you got, if you volunteered for one. It's more or less that code, except for main, but that way it compiles. Question, is that valid C++ code? Just shout out yes or no. Yes, and what does it do? It does nothing, and the genius part is it does it by getting downcasted to a function pointer. But we will see about this later. But it's valid C++. Let's talk about more specific things. Here I have a code fragment which has a const star string, and because I rarely have such a huge cinema full of people. So let's do this the proper way. What is the char string spelling here? Hello, Code Dive. Oh, come on. It's early in the morning. Let's do that again. Hello, Code Dive. All right. You're used to watch movies here. I see. So it prints that string, and after that we have that string, and after that we have the lambda, which captures by reference, and in its body it has a printf printing out that string, and it's invoked directly afterwards. Let's see what's behind this part of code. As Raphael mentioned in the introduction, I'm also the author or creator of C++ Insights.io. And quick question, who of you has heard about C++ Insights? Just raise your hands. All right, that's great. So for all of those who haven't heard of C++ Insights so far, it's inspired by Matt Godbolt's Compiler Explorer. You put in your source code on the left and you get C++ code out on the right. It's brilliant, right? It's an excellent selling point. Putting out C++ code on the left, getting out on the right, $1 million project. So what happens here is the compiler adds stuff to your source code while creating the AST, while parsing your source code. And what C++ Insights shows you is all the things the compiler adds for us during creating the AST. And if I now transform this code part here from the slide, then we can see, as this talk is about lambdas, we can see what a compiler creates for us is a class. This is the so-called closure type. This is the reason why we only can capture lambdas with auto, because we don't know the type. And in this case, the name of the lambda is made up because the compiler doesn't bother to create one because it doesn't need to. So that's one statement where you can see that the compiler only does the necessary work, and only of that the work that really is required. In this class, we can see that the compiler gives us a call operator. That would be this method here. And in that call operator, we find our function body. That's what we've written on the left. After that, the compiler ensures that what I requested to capture is in this lambda. It's a private member. In my case, is a const jar array of references to that string, size of 18, which matches the size of the string I'm capturing. And then there's, of course, a constructor part constructing that whole thing. And then below there, you can see this is when the lambda is invoked. There directly, the call operator is called. This is more or less the magic behind lambdas. And if you're asking me, I really like it. I think it's brilliant. I have the ability to write such less code on the left side. What comes out on the right is what I can also write. It's no magic, but it's just fantastic that I don't have to write all this boilerplate code. I like this. So, question for you next. While I developed C++ Insights, initially it did a bad job with lambdas. It crashed or did not show all the things. So I spent some time in improving that, and I thought about all the ways where lambdas can appear such that I can handle them correctly. This is a very short example. And my question to you is, and it's not related to what you're daily doing, or I'm not encouraging you to change your coding style tomorrow. It's just a fun question. In how many places can lambdas appear in this piece of code if you're not applying them recursively or in each other? Just shout out numbers. Let's say from 0 to 10. 3. We have 3. Do we have something else? 6. 5. Oh, now the countdown is broken. Okay. 5, 6, 7, 3. 5 is the correct answer. You can do this. You can, of course, absolutely insane, use a lambda to initialize the variable x. Senseless, I know, but it may have more meaning in different contexts. You can use in your for loop for the initializer, use a lambda to just print out something or initialize something once again. You can use a lambda to check whether the loop condition is still valid or not. You can then use a lambda to once again print something out in the post statement of the for loop. And you can have wrapped this printf in the for loop's body into a lambda. It's senseless, but it also shows in how powerful lambdas are, because they can appear in so many places, and that's what it makes initially, or what it made it initially hard to get them right. So 5 is the correct answer here.
I'm sorry, but you can have a lambda for a return statement from main, which is missing.
So the question or the comment is, I can have a lambda for written main, which you say is missing.
That would be 6 lambda.
A 6th lambda. I can define main as lambda, you're saying. Okay, I learned something today and I'm giving the talk. Thank you very much. I try this out later. So then 6 seems to be the correct answer. See, I have to improve. Okay, now about capturing. This is a small piece of code. I have a variable x outside of main, and then inside of main, I have a lambda which pre-increments x. And if you're looking closely, you can see multiple things. First of all, this lambda is directly invoked after it's created, and it has an empty capture list. Yet I claim that thing compiles. If you peek behind the scenes once again with C++ insights, if I do the transformation, if the tool is able to do the transformation, it's a good indication that the code compiles. We can see, okay, we have disclosure type below here. Everything is nice and fine. And in fact, there is no private member, but it contains x. And the reason for that is that x, in my example, is a global variable. A global variable is accessible everywhere because it's not static. I can access it from another compilation unit, things like that. And that's where the compiler is just generous with us. There is no need to capture this variable in form of a class member in this lambda because it's accessible anywhere, everywhere. So this is one time where the compiler helps us to write nice code, but also be efficient, because it would be, well, not reasonable to create a new member here. However, there are cases where you like it to be a member because you may like to keep that value at the time you created the lambda or invoked the lambda. And the interesting part is you cannot easily force the compiler in capturing this in the class. If I say it's a copy capture, I'm capturing, compiler still doesn't bother to capture it inside of the lambda. And even if I say capture by reference, which would defeat the purpose, compiler still doesn't do it because it's just more efficient to not do it from that perspective. So as I said, with the example on the shirts, lambdas can also be used together with function pointers. In this case, or in that case, you need to use a captureless lambda. Then we can assign it to a function pointer. That is interesting if you're dealing with a legacy API where you may like to assign this lambda to, then this gives you the ability. And if you look behind what's happening then, if I do the transformation here, then we can see something we saw on the example before. If I have a captureless lambda, as in this case, the compiler creates additional methods in the class for me. This one is what is called a conversion operator, and it returns this underline invoke, which is a name the compiler picks. And then I have here this static method inside the class, which is this invoke. It takes two parameters, like I declared it for the lambda itself here, and it contains the same function body as the call operator. And with that, I can assign that thing to a function pointer. As said, that's nice when you're dealing with legacy APIs. By the way, if you have any questions, just shout them out. We will somehow manage to get them through, but I can barely see anything after the fourth row or so. Which makes the next part interesting, because I have a question for you. Here I have a main function with three variables in it, a, b, and c. A and c being of type jar, a and c being of type jar, b being of type int. And then I have a lambda which captures everything it uses by copy, and it senselessly uses a, b, and c in that order, just invoking it with a semicolon. It will result in a lot of unused variable warnings in your program if you have a sufficient warning level. But my question to you is, assuming that you're dealing with a 64-bit platform, what is the size of this lambda? Just give me a number. 6. 9. Okay, count up this time. 16. 8. 12. Thank you. 12 is the right answer. Through padding rules, which are the same for lambdas as for structs, because it's a class behind it, the size of this lambda due to the arrangement of the variables is 12 on a 64-bit platform. I can influence that if I just reorder the captures. On this slide, it's the same as before, just in the lambda, I'm not saying A, B, and C, I'm now saying A, C, and B. That reduces the size of this lambda down to 8. And because I've been a long time in the embedded industry, I care about such things, even if they're seen tiny. Whenever someone tells you something like this, you probably should ask, is it valid C++? Is it standardized? And this is what the standard says. An implementation may define the closure type differently from what is described below, provided this does not alter the observable behavior of the program other than by changing the size and/or alignment of the type. Well, okay. You're not allowed to observe the behavior I just shown you. I'm sorry. It works on all the major compilers, but you should not rely on it. For now, it does the job right. I can imagine that in the future, compilers may rearrange the variables inside of the closure type more efficiently for such use cases, but I'm not aware that one does so far. If we are moving to C++ 14, we have the generic lambdas. And this here is a generic lambda, so all the time you're seeing auto as a parameter type. It's a generic lambda. And the good thing here is it enables me to write more generic code because I can formulate this lambda once, write it once, and then I can use it as shown here either with 2.0, which is a double, or just with 2, which is an int. I can invoke it, it will do the right thing. And if you peek behind the scenes, and look at this in C++ insides, then we can see what that thing does is that my call operator now becomes a template, a method template. In my case, because I only provided one, or the lambda only requires one parameter here, I only have one type template parameter, and we can see below here, because C++ Insights also shows you all the template instantiations, I get one instantiation for an int and one for a double. So once again, I'm really impressed how easy sometimes things can be added to the language, and they help us to write, once again, less code. What can you do with generic lambdas? Now that we are knowing that's a template, we can do things like this. We can use C++ 17's context brief together with decal type to get back the type, which was formerly deduced by auto, to say, okay, if that type is the same as a double, then I'm not multiplying it just by 2, but I'm multiplying it by 2.0 to reflect that I'm now doing a correct double multiplication. And of course, depending on what's else calling this lambda, my second line, the else case would be wrong because, well, multiplying it just by 2 might not be sufficient for every type. But you can now be more specific here about your types, because essentially you're in a template. Even that's you've written a lambda, it's a template now. Now this is something which caused a few headaches since we received lambdas in C++ 11. I call it a dangling reference trap, which partially gives probably away what I'm asking about. I have a function here, func. It has an int x in it, and then I create a lambda. The lambda captures by reference, and what it does is it calculates x times x and returns the result. And then in the last line of this function, I'm returning this lambda. Question, is that good? Wrong. As a consultant, that's excellent. Now you can expense debugging hours. Correct answer is no, it's not good, because essentially you're returning a reference to something which is on the stack and it's not longer there when you returned that thing. So you should never return a lambda that captured something by reference. But the more deep question is, what does the standard say? Is this undefined behavior? Who thinks yes? Who thinks no? Okay, there's a large middle part sleeping or watching on YouTube the other live stream, right? Okay, this is my probably favorite quote from the standard. This is what the standard says. If a non-reference entity is implicitly or explicitly captured by reference, invoking the function call operator of the corresponding lambda expression after the lifetime of the entity has ended is likely to result in undefined behavior. Isn't that great? I mean, with undefined behavior, it can work, but it has not to. It can break any time in the future. And now you have likely, which means, well, it can, but you don't know. Brilliant, right? Brilliant. I believe there may be an architecture out there which can deal with, because different stack handling can deal with this, so that's why it's only likely undefined behavior, but on most platforms it is just simply undefined behavior. But it's a great part in the standard. So now a new colleague comes in and different requirements. Now we need to allocate this variable x on the heap. So someone was able to squeeze in a new here, plug in a couple of pointers. Also the calculation inside of the lambda was correct, and beautiful, nice code. Still capturing by reference, still capturing by copy, so I don't return anything I captured by reference. What do you think about this code? Yeah, it's a tiny one, so it can survive a long time. But essentially it's correct, it's a memory leak, because I'm not deleting what I've allocated. It's a simple to solve problem, right? So sort the intern, and, well, what's missing is the delete. So plug in the delete. Okay, people told them that he should not capture by reference, because that's unsafe. He captures by copy, so that's safe. So I have to delete the pointer because otherwise I'm leaking memory. Brilliant, right? So now no memory leak, but I'm still back in the undefined behavior world because now I'm pointing to something on the heap which is not longer there or does not longer belong to me. We can fix this, of course, with using C++11's smart pointers, shared pointer, or unique pointer, for example. Let's talk a little bit more about captures. Here I have a class test which has one int member called a, and inside of the constructor I create a lambda which captures a by copy and adds 2 to a and returns the result. Then I'm the printf guy, so I use printf here to invoke the lambda and print out the result. And just because I can, between the two printfs, I'm pre-incrementing a by 1, and then print out the lambda once more. Question to you. What do the two printfs print out in numbers? And let me help you so far because it's early in the morning. 2 plus 2 is 4. I just checked on my iPhone. Two times 4, you're saying. Okay. Then there are a few people who pretend to sleep so they can claim later that they knew it better. It's of course 4 and 5. Why wouldn't it be, right? Why is it 4 and 5? It's 4 and 5 because what you're doing here is maybe not what the compiler thinks you like to do. We are capturing a here by copy, but a is not a simple variable, and we are capturing by copy. And what do we write? We omit it usually before this a. It's this arrow a. And what happens here is that the compiler captures our this pointer by copy, because that then contains a. But because it's only a pointer which is captured by copy, we see the increment of a inside of the lambda. So we can fix this or can improve it by using C++17's star this or dereference this, because now I'm capturing the object this, not as a pointer, but as an object. Now you're correct, and the answer is 4 and 4. This is a trap you can occasionally find yourself in. This is a different way of doing this. It's safe now. I dropped a few parts of this full example, and the question is related to the size. How does this now affect the size of my lambda? And if I go back to C++ Insights, and I transform this, then we can see what a lambda captures is in fact what I told you, it captures the object test, which is partially okay. For me, it means that I'm still capturing B, because B is a member of test, so I'm capturing A and B because I'm capturing the whole object. In pie chart terms, I'm capturing twice as much as I need in bytes, so that sounds bigger. In bytes, it's okay, but it's still more than I require. And for embedded systems, if they are small enough with their constraints, then that can be an issue. So it works now, but it still has some drawbacks. And one way out of this is using C++14's init captures, because we there can say that in the capture list we create a new variable a1 which is initialized by a, and a1 is then accessible inside of the lambda. And now I am sure that I only captured the one int I need. You can, by the way, also say in the capture list a equals a. It's a readability thing, and I do not claim that a1 is so much better than a equals a. But just to point out, you can have here a equals a, which makes it hard to read, but it may also give your idea to a certain reader that there is no difference between a and a. It's just that you need to do it that way to not capture the entire class. And if I transform this in C++ inside, then we can see what the lambda now has as member, as its only member, is in fact the int member I requested, which is called a1. So this is the most efficient way you can do this. And imagine in the example before, capturing the class, that may not be the worst thing in the world, but if your class has more members than just the int and maybe more complex members, let's say capturing a couple of std strings there, and they have to be copied, they need to allocate their memory and so on, and you just need that one string, then it creates a lot of resource usage, which is just unreasonable. So this is the best way you can do it. This is another question to the size of the lambda. It's more or less the altered version from before. I have in my constructor of the test class now additional const int variable called size initialized with 2. And then I have a lambda that captures once again everything by copy it uses. And this time, except from the fact that it returns a plus 2, it creates an int array called x, which is of the size from this outside size variable. Let's make the question easy. Is this size variable captured inside of the lambda or not? Who thinks yes? Who thinks no? Someone later has to explain to me what the rest thinks. But thank you. It is not captured because it's not ODR used. And this is once more where the compiler is really good to us. Only the things that required to be captured are captured. So if I do the transformation here, we can see, yes, I get this array in the call operator's body, but all that is captured as member is my pointer to this here. So once again, compiler is on our side. Don't capture what's not necessary. What's next? Here I have a couple of lambdas from A to F and a std string called foo, and all the lambdas do either capture by copy, by named copy, or by named reference. Some of them do print out the string foo, others don't. Assuming you have a smart compiler with the highest warning level, question is, how many unused variables warnings will you get from your compiler? Let's say give me a number from 0 to 8, and whoever says 8, please explain where the 8th come from. 2, I have. 1, 7. 6, okay, we are in the countdown mode. 5, So many answers. Wonder what your compiler's doing. Correct answer is 3. And I walked you through to this. So let's look at A. In A, I capture by copy, and I use foo in the printf. What happens if I capture a string, or if I copy a string to be precise? The copy constructor allocates new memory for the destination string and copies over from source to destination. This is, from a compiler's point of view, in this case, a side effect, which means that usually we like to see the effect that we copied a string, so the compiler cannot optimize this copy away because it's observable. So that's why A does not trigger an unused variable warning. B, on the other hand, well, it's an empty lambda capturing everything it uses while it doesn't use anything by copy, so that gives you an unused variable warning. C essentially is the same as A, just that this time I specifically capture foo by copy. D is interesting. It's interesting because some people say that you should always use named captures to be precise what's being used in the lambda's body and so on later. And in this case, I don't use foo in the lambda's body. But because of the copy construction of the std string I chose here, I still get a copy. From a compiler's point of view, you can think it like the compiler probably thinks, well, you're a fool doing this, but if you really insist that I capture this foo variable for you, well, I do so, sure. It's not adverse as using reinterpret cast anywhere, so I'm happy to capture that. So if you request it, you get it, regardless whether you're using it or not later on. Then following is E and F, which is a capture by reference, so there is no copy involved, so the compiler can tell you about the unused variable. So this is the places where you get the unused variable warnings. It's B, E, and F. And I think that's worth to know because I've seen such lambdas there. They are looking innocent because they are not invoked everywhere. And sometimes the code I've seen is that the lambda was created for debugging purposes and it was only invoked if some ifdef debug macro was enabled or whatever code path was triggered. And the impression was that this lambda doesn't do anything, but it's wrong. Every time you pass such a lambda, it does in fact copy. If it's a small string, doesn't bother you much probably, but if it's a larger string, let's say string contains the Lord of the Ring books, then it may take up some time. This here is C++ 17, and I mentioned with C++ 17 earlier, we got now const per lambdas. And const per lambdas enable us, for example, to have here a const per int array called R, which is of size 5, and then a const per bool called all-even, which invokes the std all-even function or algorithm, which compares all of or checks for all of the elements in that array with a lambda, whether the value at a certain index is even or not. And then it returns that thing. So that can all happen at compile time. And if you are now asking yourself why I gave you that gray code here, it's because I'm really cool and I know how to copy from CPP reference. The sad thing is, lambdas became const expr with C++ 17, but unfortunately, not all our algorithms are const expr. There are way more const expr algorithms with C++ 20, but for the 17 case, I had to copy from CPP reference, in that case, the algorithm and add the const expr keyword in front of it. So, in C++ 20, the same code looks like this, because I can drop all the copy of the std algorithm, I can use the regular algorithm header and write it like it's shown here. The other benefit you can see if you are a fan or like std array is now also const expr because the members begin and end are defined to be const expr, and now I can switch from a raw array to a std array and using that also at compile time. So 2 additional things that came in with C++20, begin and end, are const expr now, and way more algorithms are const expr. I think we've missed only a few. How can we use lambdas? This is an example from C++ Insights. When generating code, a common task is that there's a function defined, there's probably a call to a function, there's an if statement. All the time there are parentheses around things or curly braces to mark a body, to show the parameters or function definition. So initially I had all over the place in the code like, oh, do I need a curly brace or do I need parentheses? Is it opening or closing? And so on. So what I then did is I extensively used lambdas and wrote this function template here, wrap in parents or curlies, don't mind the spelling error. And it now enables me to have that code in a single place, which makes it much more maintainable, and it dropped a lot of lines of code in the code base. And what I'm doing here is that I'm just saying whether it's parentheses or curly brace I need. The code then handles the insertion of before and after, and with the lambda I can inject the actual string or code part I need to go in between the braces. That's excellent. The next thing I found in the code base is that I have my own for each arc algorithm. You probably know the stood for each algorithm. In that case, it's specifically for each argument, because if you're dealing with arguments, it's a simple rule, you know that. There is no comma before the first argument, and there is no comma between behind the last argument. So you need all the time to figure out, if you're generating the code, whether there's a comma required or not. It's easy for us humans, and it's easy to write it in code, but it was once again an example which was spread around the code base because I needed it in a lot of places. And what I did here now is partially the same what the stood for each does. I have this stood each for each arc function template, which loops over the arguments I passed in and takes care of inserting the comma if required or not, which once again makes the code at the using side much more readable and dropped a lot of lines of code. This is code which we are able to write now. It's not something new in a general sense. Other languages did such a pattern earlier because they earlier had lambdas. I think it's coming from Java or JavaScript, and there it's called immediately invoked function expressions. And what I'm doing here is I like my variables to be const. And in this case, it's not easy to make that stood string name const, because it's initialized either with something which has operator in its name or just with the function or method name. So 2 possibilities to initialize this stood string. Typical example is don't make it const, pick the more likely case, initialize it with that, and just in the other case do a different initialization. You can also use the ternary operator to do this initialization, but it doesn't, at least to me, look readable. So with this immediately invoked function expressions, you now can have a way to make that stood string const, which I prefer, and have a nicely written C++ statement inside. And what I'm doing here is that I create a lambda which returns a stood string. This is one of the cases where I needed to use the trailing return type, because once I return a stood string and the other time it was in the beginning at least a char string. And then the lambda is directly invoked, so whatever it returns will go into this stood string, and initialize that to string such that it can be const. I really like this pattern. Another place where it can be used is something like this. I deal a lot with POSIX API, and here I have a function read data which takes a C++20-like span as a buffer, and then it opens a file, it returns a file descriptor, and then I check whether this open was successful, so the file descriptor is not -1, it's greater than. If it's -1, I return maybe the file was not there or whatsoever. I return 0 because I couldn't read anything from the file. But if the call was successful, file is open, I next do a read into the buffer up to the size of the buffer from this file. And after that read, I once again check, was that read successful or did it fail? -1 in the POSIX API implies that something failed. So if that's the case, I return once again 0 because, well, couldn't read anything from the file. If not, then the read was successful, the file is truncated, closed, and the size that was read is returned. Who does spot the bug? See 1 hand, 2 hands probably, 3 hands, 4, okay, going up. So what's the bug? Just yell it out. Unclosed file, because I didn't close the file when the read was not successful in line 13. I'm just returning there, which is in fact something that happened very early in my career, and it can take a long time until you realize it because the kernel has a lot of file descriptors, 1024 or 4069, so depending on the frequency, it can last for some time. So I'm interested in a way to fix this in a general case and in a more stable and robust case. Let's say I introduce a yet unknown type which is called final action. I create a variable out of this type and I pass a lambda to this final action thing while creating it. And that lambda does the check. It checks whether the file descriptor is equal to -1. If not, it closes the file because obviously it was successfully opened. That means that I can drop. We will peek behind what the final action is. That means that I can drop the close in every other place. I do not need longer to care about my return statements. I can drop the close everywhere and just return, which makes this code really easy to be changed or altered or increased whatsoever. So, and the implementation of final action is this. It's a class template called final action, taking one template parameter t. It stores in maction as a member of type t whatever is passed into it. It tries to forward into maction whatever is passed to the constructor. And then, and that's the brilliant part, in the destructor, it invokes the lambda. And with that, every time we are leaving the scope, that lambda is invoked and ensures that my file descriptor is closed. Nice and easy. 14 lines of code. They work. If you're interested in a bigger solution which is capable of doing more, I suggest the guideline support library. There's at least the Microsoft's implementation which can handle other cases as well and copying that thing and so on. But for starters, this is what's needed to clean up the resource here. With C++20, we will get what is called lambda capture pack expansion together with move or forward. So what I'm doing here is I have a variadic function called invoke later, which takes an arbitrary number of arguments. And in that function, I'm creating a lambda which is directly returned, which captures all the arguments which were passed into the function, into the lambda, to call function with these arguments later. And before C++20, I was not able to apply stood forward here to all the arguments for the init capture. Okay, I had to copy them before or find other tricks, other ways. And with C++20, I now have an efficient way to be in more places perfect forward, correct. I can now just forward the arguments I received from the invoke later function into the Lambda without unnecessary copies. That's nice. Another thing, I mentioned that before, is that we now have templated Lambdas. And templated Lambdas solve a problem I'm illustrating here. Yes, with C++14 I can write generic Lambdas, and they make these two max calls working. So what I'm having here is a Lambda called max. It takes 2 parameters. It tries to figure out which one contains the greater value and then returns this one. Simple. And then I have 2 calls to this Lambda, one with 2,3 and the second one with 2,3.0. And 3.0 is a double, so in my opinion that should not easily compile, because now I am, well, giving an int and a double in there, so I'm mixing types. And there's no easy way to prevent this, except if we are thinking back to the context per if and the same decal type stuff. But with C++20 we will have templated Lambdas. Now I can write the angle brackets after the closure declaration and say, for example, type name t. And now I can mandate that x and epsilon are of type t. Not any type, no t. They both have to be of the same type. And because we are now once again talking about templates, the second max call in line number 9 does not compile anymore, because there are no implicit conversions when it comes to templates. And if we are looking about this in C++ insights, then we can see there is no big difference to the generic Lambdas, because our call operator is still a method template. The only difference now is that I can say what the type is, and that both types are of the same, or both arguments are of the same type, which is something I cannot do easily with generic Lambdas. So, but behind the scenes, nothing special compared to the generic Lambdas. What I can do with that is I can say, okay, my Lambda takes a std vector of type t. It's something I couldn't say with the generic Lambdas before. And just to highlight this, it's not limited to type parameters. You can also apply non-type template parameters. As in the second example, I can also say that my Lambda takes a std array of type int and let the compiler deduce the size of the std array that is passed in. So I can also use non-type template parameters together with that. One more thing that comes in with C++20 is something that tries to solve or make this code a little bit nicer. I have a std map here, and I like to apply a custom comparison operation. And for that, I write the compare function as a Lambda, of course, before the std map, just to then say in the declaration of the std map, decal type of compare, to get back the type of the Lambda I created before. So that seems first a little bit unnecessary, and secondly, the compare function on line number 1 leaks into the adjacent scope. And it's probably only required and used here. With C++20, we can use captureless or default constructible Lambdas in that case inside of a decal type expression, which makes me able to move that Lambda I had assigned to compare before directly into the std map. To this day, I'm still undecided whether I like the syntax, and I think it's readable, but it makes it more clear that these things belong together. Now that we talked a lot about Lambdas, there's a question about overuse in Lambdas, and if I remember from Victor's talk yesterday correctly, he mention that since C++11, people started to squeeze in lambdas everywhere in the code base. And so did I. I found out when I prepared the talk. This is once again an example from C++ Insights. And if you're looking closely, what I'm doing here is I have a bool, const bool, is list initialization, and to initialize that bool, I have a lambda which captures by reference, and it essentially returns a bool. So it's nice, but this is nicer without a lambda, to be fair. So I think I fixed the code in the meantime. But yeah, there is a potential to do that. If you're interested in lambdas, there's a lot of work of other people out there. I'm not the only one. There's a really great talk by Björn Faller, who was later this day another talk. It's called High-Ordered Functions for Ordinary Developers. He gave it at least at Meeting C++ and other conferences. And there are blog posts there are YouTube videos just about lambdas. So there's a lot of fuss about lambdas. All right. I talked a lot about lambdas, and the time more or less is up. So there are just 3 more words I like to say to you, and that's I am fertig. Thank you.
Ja, fantastisch, sehr schön. Dankeschön.
Danke.
Und jetzt Fragen und Antworten, also known as Q&A. So if anybody's interested, and please use English for the sake of the room.
Or you can use German, I can translate.
Floor is yours. Any questions, please join us here downstairs.
Actually, I have a question. Is the CPP Insight actually somehow getting into the compiler to show what the compiler really, how the compiler sees the lambda, or are you generating the code based on the standard, what it's supposed to be?
Okay. Yeah, that's an excellent question. Always question the tools you're using. So what C++ Insights does, it's a Clang-based tool, and it uses the AST that Clang generates for you when parsing the code. So for the lambda, it goes that Clang, in fact, generates an AST node with the class and everything just without a name. And I have to fiddle a bit around for the constructor. So the compiler, at least Clang, doesn't bother to create an AST node for the constructor. So there is a little bit made up stuff. But in general, I try to stick as close to the AST as possible. And most things, surprisingly, are there. So I try to not squeeze in my knowledge because that could be wrong.
However, it means that it works only for the, well, it shows what Clang would do, but not other compilers.
Yes. Correct. So it shows the code with the eyes of Clang, plus with in some cases with the eyes of the standard library. Per default, C++ Insights on the web page uses libs.c++, which is the GCC library, but you can also use it with libc++. So you see implementation differences there. But yes, GCC in fact can do things different as long as it's in the range what the standard defines. But yes, yeah.
And I have another one. In our code, when we are using lambdas for standard algorithm, we often tend to get them out of the argument and name them as a variable, meaningful name, just to make the expression shorter and somewhat more readable. But then there is a problem. There are 2 schools. Some people use auto for the variable, and then probably, if they remember it, move it into the algorithm, or the other school uses const autoref and then just passes the argument without moving. Which one is better, or is there any difference actually?
Well, it's probably hard to tell. I would say it's mostly a matter of taste from what you described, and I understand that there is the risk that you're forgetting to move it with the first version. I personally a little bit prefer not to have to pick a name, because for me it's hard to come up with a proper name just because you like to feed it into the algorithm. So, but that's my personal thing, and it has nothing to do with performance. So if you are not missing the stood forward or stood move, from what I understood, I think they are equivalent in terms of performance.